Welcome, everyone, to TechDaily.ai. I'm your host, David, and I'm joined today by our resident expert, Sophia.
Hey everyone, I'm really glad to be here. We have a lot of pretty complex engineering to break down today.
We really do. But before we get into exposing the invisible physical footprint that your smartphones are generating right now, I need to let you know that you can sponsor this podcast for just $25. Your message will be featured across major platforms like Apple Podcasts, Amazon Music, Spotify, and more. If you're interested, visit TechDaily.ai to get started today.
It's honestly a great way to reach a really incredibly curious audience.
Yeah, definitely. So I want to start by asking you to just look at the device you are using to stream this audio right now.
Right, your phone, your laptop, whatever it is.
Exactly.
Yeah.
It's so easy to focus purely on the software, right? We interact with these digital tools all day.
Yeah, like training local AI models, downloading massive 4K video files, compiling code.
Right. And because all that processing often happens remotely, we treat the output as, well, essentially weightless.
Like it just exists in the cloud.
Exactly, the magical cloud. But the reality of our digital footprint is relentlessly physical. I mean, every compute cycle happening remotely generates a proportional amount of thermal energy.
It generates physical heat, a lot of it.
Yeah, and so today we are examining the localized physical impact of these massive data centers that power our digital infrastructure.
And how they are fundamentally altering the microclimates of our cities.
Right. And we'll also get into the just highly resourceful methodology researchers are using to map these invisible thermal plumes.
The urgency here really comes down to the sheer density of modern compute. We aren't just talking about, a few warm server racks in a basement somewhere.
No, not at all.
We are talking about hyperscale facilities.
Wow.
From a thermodynamic perspective, they basically function like industrial power plants in reverse.
Wow. Power plants in reverse. I like that.
Yeah, because they consume massive amounts of electricity, and their primary physical byproduct is just pure heat.
And this byproduct is fundamentally altering neighborhoods located like right down the street from these facilities.
Exactly.
The scale of this infrastructure buildup is it's what initially caught my attention, because U.S. data center capacity is projected to more than double by the year 2030.
Double in just a few years.
Right. We are dropping these million-square-foot facilities into suburban and urban environments at this unprecedented rate.
And to prevent the thousands of servers inside from, well, literally physically melting down under the computational load, operators have to rely on massive air-cooled condenser arrays.
Right. So how do those actually work?
So those arrays are essentially colossal heat exchangers. They circulate a fluid or refrigerant through the server racks to absorb the thermal energy from the processors.
Okay, so it pulls the heat away from the chips.
Right. And then they pump that heated fluid up to the roof or the exterior of the building. And then giant industrial fans force ambient air across the condenser coils.
Which transfers the heat from the liquid out into the atmosphere.
Exactly, and the result is this continuous high-velocity blast of heated air that is expelled directly into the surrounding environment.
And we aren't just talking about, like, a slight warm draft here.
No, definitely not.
The air, these arrays' exhaust, is typically 14 to 25 degrees Fahrenheit, hotter than the ambient and outdoor temperature.
Which is wild if you think about it.
Right, so if a facility is operating in a region where it's already an 80-degree summer day, those fans are continuously pumping out millions of cubic feet of air that is, well over 100 degrees.
And that volume is key. I mean, the waste heat generated by just one single hyperscale data center can easily surpass the combined thermal emissions of 40,000 residential households.
Oh, wait, 40,000 households from just one building.
Just one building, yeah.
That is insane. I mean, are we essentially building the equivalent of industrial-sized space heaters directly adjacent to residential neighborhoods?
That is exactly what we're doing, because that exhaust doesn't just disappear.
Right, it has to go somewhere.
It forms a thermal plume. It's this distinct, continuous current of hot air that gets carried by the prevailing winds directly into downwind areas.
And that plume has been shown to raise local ambient temperatures by up to 4 degrees Fahrenheit, right?
Yeah, and 4 degrees is a highly significant delta when you look at urban thermodynamics.
Okay, but let me push back on that slightly, though.
Sure.
If a data center is built in a place that already experiences extreme heat, say, somewhere hitting 100 or 110 degrees in August is an extra 4 degrees really going to fundamentally alter the livability of the area.
I mean, people think that, yeah.
Right. Doesn't it just kind of blend into the existing baseline heat? I mean, hot is hot, right?
It's a really fair question, but the impact of heat is entirely nonlinear.
Okay, what do you mean by nonlinear?
Well, an additional 4 degrees doesn't just make you feel slightly more uncomfortable. It fundamentally alters the efficiency curve of every other system in that microclimate.
Oh,
Yeah, for instance, think about the air conditioning units in those downwind residential neighborhoods. They operate based on temperature differentials.
right.
So when the ambient air outside a house gets 4 degrees hotter, the residential AC unit loses thermodynamic efficiency. It has to run longer.
Which means it's drawing more power from the local grid.
Exactly. And paradoxically, it's exhausting more of its own waste heat right back into that same neighborhood.
Wow, so you end up in this, like, compounding feedback loop.
Yes, exactly.
The data center strains the power grid and heats the neighborhood, which then forces the neighborhood to draw even more power from the strained grid just to overcome the data center's heat.
Precisely. And this is a hazard that city planning commissions just haven't historically modeled.
Why not?
Well, when zoning boards evaluate a commercial development, they look at variables like traffic congestion or noise decibels or, raw electrical draw.
Sure, the obvious stuff.
Right. But the continuous directional exhaust of physical heat, that hasn't been a primary metric for industrial zoning.
That is a massive regulatory blind spot.
It is. And to change that, researchers first have to definitively prove the plume exists, map its exact boundaries, and then separate it from all the other heat sources in a city.
Which brings us to the methodology. Because isolating a single heat source in an urban environment seems, well, almost impossibly complex.
It's incredibly difficult.
I mean, if you think about the physical makeup of a city, it's essentially just a giant, chaotic radiator.
Right.
You have acres of dark asphalt acting as a thermal mass soaking up solar radiation. You've got concrete buildings trapping heat in urban canyons, and like thousands of internal combustion engines stuck in traffic.
Yeah, there's heat coming from everywhere.
So proving that a temperature spike in a specific neighborhood is coming strictly from the condenser array of a server farm, rather than just the busy intersection next to it, requires incredibly precise telemetry.
And that specific challenge of isolation is exactly what researchers at Arizona State University, led by David Saylor, set out to solve.
And they purposefully chose the Phoenix metro area to conduct this research, right?
Yeah, which is pointedly the hottest metro area in the U.S.
Right, an extreme urban heat island.
Exactly. The logic is, if you can successfully isolate and track a thermal plume in the chaotic, high-temperature environment of Phoenix, well, you can validate the methodology for virtually any other city.
That makes total sense. And their physical setup to capture this data is just brilliant.
It really is.
They basically built these mobile sensor platforms to act as thermal storm chasers.
I love that analogy. Thermal storm chasers.
Right. The research team mounted high-accuracy sensors onto vehicles and drove them in structured traverse patterns around the perimeter of the data centers and then deep into the downwind subdivisions.
But a critical detail here is that they strictly utilized electric vehicles for the data collection.
Right, EVs. Why was that so important? Oh, wait, I guess it immediately eliminates the local contamination issue, right?
Yeah, using EVs was an absolute necessity for the integrity of the data.
Because if they had run these traverses using standard gas-powered cars, the radiant heat off their own internal combustion engines, plus, the 300-degree exhaust constantly venting out the tailpipe.
Right, it would completely corrupt the microscale temperature readings they were trying to capture.
It would ruin their own data. That's so smart.
It removes the most immediate anthropogenic heat source from the equation. Because when you are trying to map a thermal plume down to fractions of a degree, your collection method just cannot alter the environment it is measuring.
Makes sense. But beyond the vehicles themselves, the specific hardware they utilized for the thermal logging is where the engineering really shines.
Oh, yeah. They relied on four-wire resistance temperature detectors, or RTDs.
Okay, for anyone who hasn't dug into sensor hardware recently, what is an RTD?
So an RTD measures temperature by tracking how electrical resistance changes in a metal element, usually platinum, as the ambient air gets hotter or colder.
Okay, so as the platinum heats up, the electrical resistance increases in a highly predictable linear fashion.
That's the basic mechanism, yes. But The critical distinction in their setup is the use of the four-wire configuration.
Because the wires connecting the sensor outside the car to the logger inside the car also have their own electrical resistance, right?
Exactly. And that resistance fluctuates based on the temperature inside the car or just the length of the cable.
So if you just use a standard two-wire setup, the logger can't tell if the resistance change is coming from the platinum sensor outside or just the copper wire heating up inside the door panel.
Exactly the problem the four-wire setup solves.
How does it solve it?
By dedicating two wires purely to supplying a constant electrical current and the other two wires exclusively to measuring the voltage drop across the platinum element.
Oh, wow.
Yeah, the system mathematically cancels out the resistance of the lead wires entirely.
That is so elegant. And that is how the ASU team was able to achieve an accuracy rating within 1/10 of a degree Celsius, right?
Yes, but it isn't just about the accuracy, it's the latency.
The speed of the reading,
These RTDs have a response time of under 3 seconds.
which is crucial because when you are conducting traverse measurements, meaning your sensor platform is a car moving through space at 30 miles per hour, latency basically destroys your spatial mapping.
Yep. If your sensor takes 15 seconds to register a sudden blast of hot air,
Your car has already traveled hundreds of feet down the road before the spike even shows up on the logger.
exactly, you would map the edge of the data center's thermal plume in completely the wrong neighborhood.
Wow, okay. Spatial resolution is entirely dependent on temporal resolution.
Precisely. The sub 3-second response time ensures that the recorded temperature closely aligns with the physical location of the vehicle at that exact moment.
And they mounted two of these highly sensitive RTDs on each EV, right?
Yeah, one protruding from the driver's side window and one from the passenger side. And they were both positioned about 2 meters off the ground, or about 6 feet.
To capture the air at human-level elevation.
Right.
Which brings up, honestly, the most fascinating juxtaposition in this entire methodology.
The PVC pipes.
Yes, you have these hyper-accurate, low-latency, incredibly expensive scientific instruments. But if you drive them around Phoenix in the afternoon, direct solar radiation will heat the metal of the sensor, giving you a completely false reading of the actual air temperature.
Yeah, the sun would just bake them.
So, to shield this high-end tech from the sun, the researchers housed the RTDs inside standard PVC T-section pipes.
Just literally off-the-shelf plastic plumbing joints you can pick up at any local hardware store.
It's a phenomenal example of engineering pragmatism.
It really is. In atmospheric science, you generally house sensors in something called a Stevenson screen, or an actively aspirated shield, to block solar loading while allowing air to circulate.
But the PVC T-pipe achieves this passively.
Exactly. The geometry of the T-pipe is what makes it work so well. It basically acts as a physical awning against the direct sunlight, preventing the metal from absorbing radiant heat.
But because the ends of the T-section are open and facing the direction of travel, the forward momentum of the EV physically forces the ambient air through the pipe and directly over the RTD element.
Right. It provides natural aspiration. The movement of the car ensures a constant replacement of the air volume inside the pipe,
guaranteeing that the sensor is measuring the true temperature of the surrounding air mass, rather than just some stagnant pocket of air heated by the plastic itself.
It's just brilliant. So the team is driving these PVC-rigged EVs in overlapping grids around the data centers, sampling the ambient temperature every 1 to 2 seconds.
But temperature data alone is completely disconnected from geography.
Right.
To build a physical map, they had independent GPS loggers inside the vehicles pinging latitude, longitude, elevation, and vehicle speed at 1-second intervals.
Which creates a really significant telemetry alignment challenge.
Because you have high-frequency thermal data on one logging system and spatial coordinates on an entirely different, unsynced hardware platform.
Right. The RTD logger doesn't know where it is, and the GPS logger doesn't know how hot it is.
So after completing hours of traverse drives, the research team had to pull both datasets into the lab and meticulously correlate them using exact timestamps.
They had to mathematically stitch the two sets together.
Like, at 14.05 and 32 seconds, the vehicle was at this precise coordinate, moving at this exact speed, and the ambient temperature was 98.4 degrees.
They literally had to rebuild the invisible thermal landscape second by second.
That is painstaking work.
It is, but that resulting map provides a highly granular empirical snapshot of the heat distribution.
Okay, but an urban microclimate is not static, right? Heat is a fluid, and it gets pushed around by wind.
Exactly. If you want to understand how a thermal plume behaves, you have to track the atmospheric dynamics moving it.
And I imagine relying on regional weather data isn't going to cut it.
No, definitely not.
You can't just pull wind vectors from an airport 5 miles away and assume that's what the wind is doing at street level next to a 1 million-square-foot server farm.
Right, because large commercial buildings alter local wind patterns. They generate updrafts, downdrafts, and localized turbulence that completely dictate where the heat exhaust actually goes.
So how do they solve that?
Well, the researchers deployed deployable weather stations within the test areas, but to capture the actual wind dynamics interacting with the plume in real time, they mounted 2D sonic anemometers directly onto the roofs of the electric vehicles.
Sonic anemometers. For those unfamiliar with the hardware, a sonic anemometer doesn't use the spinning mechanical cups you usually see on a weather station, right?
No, it actually has no moving parts at all.
So how does it measure wind speed?
It calculates the time of flight of ultrasonic sound waves between pairs of transducers.
Wait, it uses sound.
Yeah. The underlying physics relies on how the medium, the air, affects the propagation of sound. The transducers ping ultrasonic pulses back and forth across a measured gap.
Okay.
If the wind is blowing parallel to the sound wave, it physically speeds up the pulse's arrival time in one direction and slows it down in the opposite direction.
That is wild.
Mm.
So by measuring those microsecond differences in arrival times across multiple axes, the onboard processor calculates both the exact velocity of the wind and its precise vector at that specific moment right above the car.
Exactly. And this data was collected across multiple drives, capturing a variety of atmospheric stability conditions.
Because a thermal plume behaves very differently on a stagnant, highly humid afternoon compared to a dry, windy morning.
Right, like during an atmospheric inversion versus high atmospheric turbulence. The goal wasn't just to prove the heat existed on one specific day, but to capture the full aerodynamic profile of the plume under varying environmental stresses.
Which leads to the ultimate application of all this field data.
The modeling.
Yeah, they take the millions of data points, the localized temperatures, the wind vectors, the vehicle speeds, the GPS coordinates, and they feed it into a microscale computational fluid dynamics model, or CFD.
And CFD modeling is a highly computationally intensive process. You break down a physical space, in this case, the data center and the surrounding neighborhoods, into a three-dimensional grid of thousands of tiny computational cells.
This is where people often get skeptical about microscale modeling, though.
Oh, for sure.
They assume an algorithm can't possibly account for every chaotic variable in a subdivision. Like, can an algorithm really predict a random gust of wind hitting a delivery truck or the changing shadow of a tree?
Well, a CFD model isn't trying to predict the exact path of a single leaf.
Right.
It's solving fluid dynamics equations across that 3D grid to map the overarching momentum and thermal energy of the entire air mass.
That distinction is crucial. You aren't mapping the behavior of a single water droplet. You are calculating the overall current, volume, and trajectory of a river.
Exactly. The CFD model computes how the mass of hot air interacts with the solid geometry of the buildings, how it shears against the ambient wind, and where it ultimately settles.
And the reason the ASU team drove the electric vehicles around Phoenix was to gather the empirical data needed to validate this exact computer model.
Right, the real-world validation.
Because once you run the CFD simulation, and its digital output perfectly matches the real-world temperatures and wind speeds the PVC-rigged cars actually experienced on the ground.
Then you know your mathematical model is an accurate representation of physical reality.
And once validation is achieved, the researchers cross a critical threshold. They transition from purely observational science into predictive engineering.
Right. The validated CFD model can be switched into what they call design mode,
which turns it into a highly advanced stress testing environment for city planners and structural engineers. It's almost like playing SimCity.
It really is. They can use the simulation to ask complex architectural questions before millions of dollars are spent pouring concrete or deploying condenser arrays.
Right, they can manipulate the variables in a virtual environment. Planners can ask, what happens to the downwind plume if we reorient the entire building axis by 45 degrees?
Or, how does the thermal dissipation change if we increase the height of the exhaust stacks by 5 meters or adjust the pitch of the cooling baffles?
They could even model changes to the internal engineering of the servers themselves. Like, they can simulate trade-offs, like lowering the total exhaust temperature, but increasing the cubic feet per minute of air volume.
And instantly see how that specific configuration changes the heat map of the residential neighborhood next door.
It gives zoning boards the empirical tools to mandate layouts that safely vent the thermal exhaust up into the upper atmosphere rather than laterally blasting it into the backyards of a nearby subdivision.
Right. It equips local governments with the exact analytical blueprint needed to manage the physical realities of urban tech expansion.
Because, as we noted earlier, the compute demands of modern society are on an exponential curve. This infrastructure is going to be built.
It's a ticking clock, especially with 2030 approaching. If we are going to integrate these hyperscale facilities into our existing urban fabric, we have to engineer the physical thermodynamics with the same rigor we applied to the digital architecture.
We just can't treat the physical environment as a limitless heat sink. So if we look at the entire scope of this methodology, it starts with recognizing that our abstract digital demands the AI generation, the streaming, the low latency processing manifest as millions of cubic feet of 100+ degree exhaust in the physical world.
A thermal reality that alters local climates by up to 4 degrees, creating cascading inefficiencies for neighboring electrical grids and HVAC systems.
And to combat that, we looked at how researchers apply immense ingenuity to map these invisible forces.
Right.
They strip away the anthropogenic heat of traditional vehicles by deploying EVs, rig hyper-accurate 4-wire RTDs inside everyday PVC plumbing to perfectly capture aspirated air while blocking solar radiation and sync that data to the second with onboard GPS telemetry.
All while measuring localized wind vectors via ultrasonic pulses to understand exactly how the environment pushes the plume.
Which culminates in a fully validated computational fluid dynamics model that allows engineers to virtually test and alter building designs, ensuring that the exhaust from tomorrow's server farms is safely routed away from our homes.
Yeah.
So the next time you initiate a heavy computational task, take a moment to visualize the physical engineering required to dissipate that heat into the atmosphere, and the mobile sensor networks navigating city streets to track exactly where that heat ends up.
It really makes the invisible infrastructure of our daily lives highly tangible.
It does.
And it opens up a rather provocative avenue for future engineering.
Yeah.
I mean, if we are currently deploying immense resources just to safely vent this thermal energy away from our cities, how long until the paradigm shifts?
What do you mean?
Well, will upwind from the data center become the new premium selling point for real estate? Or instead of viewing a 25-degree thermal exhaust as a hazard to be mitigated, could we engineer heat recovery systems?
Oh, wow.
Systems that capture this continuous high-volume energy output and channel it into district heating grids to actually warm nearby homes or power municipal infrastructure.
Transforming the largest physical byproduct of the digital age from an environmental liability into a localized energy asset. That is an incredibly compelling engineering challenge to leave you with. Take some time to ponder how the physical footprint of our digital lives might eventually become the very resource that powers our neighborhoods. Thank you for tuning in to TechDaily.ai, and we will catch you next time.